Okay, so today we're going to talk about gravity and free-falling objects. Um, and so let me back it up right here. So we have gravity, and gravity is a force that acts between two particular objects, between two masses. For us, it's an object that's suspended in space and the Earth. In fact, the larger the object, the greater the gravitational pull. That's why if I were to go to Pluto, my gravitational pull would be significantly less than my gravity pull on Earth because Earth is a much bigger planet. If I go to Jupiter, which is 3 times the size of Earth, my gravity or my weight, and later we'll find out our weight, is actually going to be 3 times as much. Now, the person that is given credit for the concept of gravity is Galileo. And Galileo was born, or actually existed, in the 1600s. And he was a scientist. He was famous for astronomy with telescopes, but he also did a famous experiment on the Leaning Tower of Pisa. This one up here in the corner. That's the Leaning Tower of Pisa. And he went up to that very top tower and actually dropped some bowling balls, little metal balls that they use for playing bowling. And he actually dropped them, and he noticed that all objects were falling at that same rate. And he actually calculated it using some trig, and he found out that the acceleration rate that the objects fall is at 9.8 meters per second squared. And again, we have a little experiment link. So if you'll click on this little link right here, it kind of tells you about his experiment with gravity and free-falling objects. Okay? We also have something called projectile motions. And projectile motions basically is if you were to have a target and it is shot forward, it can curve, as you can see, but gravity pushes down on it, but you also have that forward force that's being acted on. So with projectile motion, you basically have two forces: a forward force that's being applied to the object, creating and having it go forward, but also gravity. Gravity over time will cause that object to fall downward towards the earth, that gravitational pull. Okay, here's one right here called air resistance. This is another force, and what happens with air resistance, it's a force, and it's actually going to naturally slow objects down. Now, if yesterday y'all had a little experiment where you dropped the book and then a piece of paper. If you were to drop the piece of paper, it catches the wind and it actually drags and it falls at a slower rate. Then it's like a parachutist or a person in the military and they're parachuting to a location, they open up the parachute, it catches the wind and it actually will slow them down. Versus than if they're just falling from the air. Okay, so air resistance is this force, and it typically will slow down falling objects. Okay, now if I'm in a situation where I did not have an atmosphere, no air molecules in there, then air resistance would not be noted. Now, another scientist, again, Sir Isaac Newton, were credited with his 3 laws of motion, but he also had the experiment or the observations about apples that were actually falling from a tree. Now, there's a little myth about he sat under the tree and the apple hit him in the head. It actually did not occur. That's an urban legend right there. But actually he did see apples that were falling from the tree and noticed that these objects were attracted to the ground, to one another by their masses. Okay? And here's that experiment, the feather and the rock. Well, if you drop a feather and then if you drop a rock, and here's the situation is an elephant and a feather. But if you were to drop a rock and a feather, we know because of the feather and being spread out, it kind of swoops back and forth. Well, the team on the Apollo missions who went to the moon actually did this experiment. They were thinking, since there's no atmosphere on the moon, what if I dropped a rock and a feather? Would they fall at the same rate? And they actually found out, and they did that experiment and filmed it, and actually both fell at the same rate. And the reason for that, there is no atmosphere on the moon, so therefore there is no air resistance. No air on the moon, so therefore there's no air resistance to slow it down. Okay, so what about in a vacuum? So if we were to take an area, take a vacuum, vacuum out, actually suck out all the air, both items would fall at the same rate. So we can simulate that on Earth, and scientists have. They've created these rooms where they sucked out all the air, dropped two objects in there, and one was spread out, and which normally in a situation would fall at a slower rate. And they actually found out in the vacuum, in the area with no air, that the object actually fell at the same, both objects fell at the same rate. Now we have gravity and weight. As we said, gravity is that attraction between two objects. Well, our weight, typically we think pounds, but our weight in here is the force of gravitational pull. If I go on the moon, my weight is a lot less than what it is on Earth due to the gravitational pull and the size of the object. And again, as I said earlier, if I go to Jupiter, my weight would be so much more because of the gravitational pull of Jupiter. So again, on the formula right here, weight is expressed as the force of G because it's gravity that is creating this force. So its weight is equal to mass times acceleration due to gravity. And acceleration due to gravity is 9.8. Remember what Galileo said, that all objects fall at a rate of 9.8. So here is the formula. Force, which is gravity, is equal to mass times acceleration due to gravity. It's very similar to the force equals mass times acceleration, but in this instance, our acceleration, we're going to use 9.8, the rate at which all objects fall on Earth. So here we have two example problems. So the first one up here, you have, and let me get my pen so we can actually calculate this and show it. Okay, so it says if a 200 kilogram dude is on Earth, what is his weight? Okay, so remember, if I draw my triangle, remember the force is up at the top. Okay, mass is over here, mass. Gravity's right here. Okay, and then the force due to gravity is up here for our weight, F of G. Okay, all right, so we're having to solve for this. This is what we want to know. Okay, his mass is 20, so let me put 20 right here. And we want to put for gravity, it's unknown. Right here, we don't see it in the problem, but gravity is actually 9.8. This is that magic number we're going to put on there. So it's 9.8. So when I calculate 20 times 9.8, 20 times 9.8, I get 196. So my weight would be 196. Okay, and because it is a force, it is measured in newtons. Okay, and so that is the unit. Let me make this more of a 9 right there. There we go, 196. All right, so our second problem is we have a rock on Earth, and it has a weight of 1,000 newtons. We want to know the rock's mass. So looking at that same triangle right here, I have up here the weight, which is 1,000 up at the top. Okay, 1,000. Okay, get that last one. Okay, so we have 1,000, and we're actually having to solve for the mass, and here's the M for mass. So you're actually have to plug in that blank number that's listed up there, which is gravity. And gravity, the known number, would be 9.8. Please remember that 9.8, it would be that number. Okay? So here it is, 9.8. So you would take 1,000 divided by 9.8. Okay, and so the mass would be 102. 102, and on that one, mass is measured in kilograms. So it would be 102 kilograms over here. Okay? And in class, we're actually going to show you how to calculate each person's actual weight. Take the poundage and convert it. So we'll do that one after the notes. All right, and this concludes our notes for today.